So from last time, we were doing variation of parameters, so we were using our same variational equation that we were using before, where this E phi is essentially the energy associated with some guess. We can write that down as like having some guess function psi rather than our exact solution. And we said last time we were going to change, so we did two different things last time with the variation of parameters. First, we finished up our example of just doing a one electron, one nucleus system, looking at hydrogen and doing variation of parameters on hydrogen rather than solving the differential equation. And we saw that we could actually get some pretty reasonable answers with a very simple function rather than having the full complex functions we see for our R and L's and our Y LMs, right? So we could write much more complicated functions, but for the ground state, we could have a pretty simple guess function. We said, okay, well, what if we wanted to do some different type of guess function? And this type of guess function is rooted in something else physical that we're going to continue with today. It's rooted in looking at building up molecules. So this is leading to something. But for now, we're just saying this is the function we guessed. Let's see what comes out of it. And we said we solved these integrals last time, and we said we could plug those integrals in, and we got this kind of mess. And we said, okay, well, we want to optimize with respect to C1, and we want to optimize with respect to C2. Last time we finished doing the derivative with respect to C1, and we had to have a couple extra things in there in order to get this more simplified equation that we have over here. And two of the things that we had that allowed us to simplify were the fact that since our Hamiltonian operator is Hermitian, H12 was equal to H21. So you can see when I was doing this the first time, and I didn't do that right, when we were doing this last time, we left it in this generic way, where each of these H's without the hats and each of these S's with the double subscripts, those represented different integrals we could do if we had to. And we're going to look at some of those integrals today by specifying the system we want to look at, but those are integrals we could do. One of the things that we could do, though, is we could simplify the fact that H12 and H21 are the same if this is Hermitian. And we could also say we could do the same thing with the S integral, which we will be calling the overlap integral later on in this class. But we could essentially say, for the guesses that we're going to be using, wave function type guesses, real type function guesses, the S12, S21, this also has to do with the fact that we're going to be using functions that are associated with a Hermitian operator. Those were two things that allowed us to simplify down so I didn't have to carry around as many terms. So I didn't have to do a C2 S12 plus a C2 S21. I could just say, oh, those are going to be the same. We could do the exact same thing, taking the derivative with respect. So the bracket, I'm taking the derivative of not just one of these sides. I'm taking the bracket of this entire equation, this side equal to that side. I'm taking the derivative of the whole thing with respect to C1. There's actually one more thing that we have that simplified. We had one more thing that simplified. We got rid of an entire chain rule term on our left-hand side because we said if we're doing this for a minimum, the derivative with respect to the energy, with respect to this parameter is going to be 0. That's because we're trying to minimize our energy. We can do the exact same thing now with the derivative, looking at the partial derivative with respect to C2 of that whole bracket. And we're going to get something that's going to be surprisingly similar. Question?
Why is it only for C1?
It's going to be true for C2 as well. These are just the things we already did.
Okay.
So when we do this C2 case, we're going to have a similar set of assumptions, except for it will be the derivative with respect to C2 is 0. The other two things will also still be true. So you're right to be thinking ahead. So we can go ahead and say I'm going to have derivative of E phi with respect to C2 times the parenthesis, applying the chain rule, plus, and I'm leaving this parenthesis blank because we're going to have the same zero trick happen here. So right, since we're going to say this part's equal to 0, whatever it's multiplied by isn't going to matter. Same trick we used last time, right at the end of class. So then I'm going to have plus chain rule E phi times the derivative with respect to C2 of this. This one I'll actually write out. And I'm already going to apologize because I'm going to erase the thing I just wrote so I have space to write this out. I'll put it here. Sorry about that. So we're going to do derivative with respect to C2. That first term is going to be a 0. Second term is going to be a C1, S12. Second term is going to be C1, S12. Last term is going to be a 2, C2, S22. And we can already see how this is going to have some parallels to the other case. I'm going to have 2C1, I'm going to have 2C2. I'm going to have S11, I'm going to have S22. And this is going to be nice because it's going to build up into big matrices. Yeah?
Should it be in the second or third term should be 2-1?
2-1. And then we'll apply our tricks, which says actually that level of specification isn't going to matter for this. But for now, it is going to matter other places. But for now, let's go ahead and make sure we're being careful with our subscripts. So thank you for that. And then this is all going to be equal to the derivative of this side. So I'm going to have a 0 term plus a C1 H12 plus a C1 H21 plus 2 C2 H22. And essentially, we can look at this and say, wow, what a mess did we just make? Or we can look at this and say, actually, when we start to simplify this, when we start to rearrange this, we can recognize the fact that I've got an equation. I can do a little bit more simplification using my same principles. I can say that the derivative with respect to C2 of the energy of phi is going to be equal to 0. Same thing we used before. I can say let's see, do I want to say that yet? Yeah. I can say my H12, my H21 are going to be equal to each other. Because they're Hermitian. And I can also say my S12 is equal to my S21, again, because of the functions we're using. And we can do this more generically without putting any restrictions. So we're using these two restrictions to simplify things. And when we do that, we're going to get essentially two equations with two unknowns. I'm going to have E phi times 2C. Actually, one more thing I want to notice before I copy this down. Factors of 2 everywhere, right? So the benefit of putting these together, I can cancel out all of my factors of 2. When I put these together and these together, again, I can cancel out all my factors of 2. So looking at just this first equation, the equation with respect to C1, with derivative with respect to C1, I'm going to have a C1 S11 plus a C2 S12 equal to C1 H11 plus a C2 H12. And then I'm going to have a second equation. So I've got two unknowns, C1 and C2. Theoretically, we can solve all of these integrals And I've got a second equation. Which is going to be, we'll make sure I don't mess this up. I'm going to write it in a little bit of a different order. C2 S22 plus C1 S12 is equal to C2 H22 plus C1 H12. And now we start looking at ways that we could solve this. And this is something I mentioned right at the end of class last time. I said, who's used a matrix in order to solve a system of equations? And there were a few hands and a lot of crickets. So what we need to realize is that there's different ways we could go about solving this. And there's different ways that we could rearrange this in order to give us some semblance of what's going on. What I'm going to do is I'm going to organize this in terms of essentially the different wave functions, wave function 1 and wave function 2. Wave function 1, wave function 2. This one would technically be 2, 1 or 1, 2. You know, those things are equal. Wave function 2, wave function 2. So I'm going to organize this in terms of where all the wave functions are and essentially write out a matrix associated with C1, C2 and all of the H11s and H22s. And essentially what we get when we do that is we get an E phi times a matrix S11, S12, S21, S22. This one we could write 1, 2 or 2, 1. I'm writing it as 2, 1 just to make the indices match with where it is in the matrix. Times C1, C2 is equal to H11, H12, H21, H22, C1, C2. Now, for some of you, I'll put a label on this for some of you. For others of you, this will be fine. For some of you, that's magic, right? The way I rearranged it looks like magic. It's not really magic, it's mathematics. Sometimes those things are synonymous for us, but this is really math, right? And if I go through and I do my multiplication through, 1 through 5 matrix mathematics. Oh my goodness, that is more zeros than I was expecting. Okay, ooh, shucks. So this is funny. I was told to be ready for you to not know how to do determinants, and most of you were okay with determinants. I was not told to be ready for you to be having trouble with matrices. Yes?
I was curious about the S12 is equal to S21. Was that due to a Hermitian operator that we used when we were deriving it, or is that just a...
It's right now, it's really going to depend on which guess functions we use. But if we're using real guess functions, then the complex conjugate doesn't matter, right? And so that's going to be really common, but it's going to depend on the guess functions we use. So this matrix that I have here is the really generic form, where I'm saying 1, 2, 2, 1. These equations are have a little bit of assumption in them. This is a little bit more generic. So let's see. I wasn't ready to do this, but let's go ahead and do a quick aside. If I remember correctly, correct me if I'm wrong, but we would take the first row multiplied by the vector. That's going to give us our first few terms, and then then our second row times the vector would give our second terms. So you see you got an S11 times a C1. That gives us that term. S12 times a C2 gives us that term. S21 times a C1 gives us that term. S22 times a C2 gives us that term. So this gives us a way to generate these two equations. And the reason it's nice is because we'll be able to, without having to go through this whole derivation process again, which we've spent an hour and a half on already, we'll be able to just formulate matrices and say these matrices will generate the equations I need to solve. Questions?
So for
So say that again.
So each vector is multiplied by the respective column. So the first vector goes into the first column.
First vector, but if you're doing matrix times vector rather than vector times matrix?
Well, maybe it's
Yeah, so I think you're thinking about if you had like a vector times matrix, like that, right? So this is really not a vector in the same way that we've talked about it before. It's going to be related to vectors, but it's representing essentially we're generating two equations from this. And then we've got the same thing over here. My H11 times my C1 is going to give me this term associated with my first equation. And my H12 times my C2 is going to give me this term associated with my first equation. Then I'm going to take my second row, multiply through. So this gives me these equations. I'm a little flummoxed at what to do next in terms of those of you who are not comfortable with this. So I might say, hey, it's nice if we can generate this from doing the derivatives and doing all the integrals for the guess functions, but let's take the shortcut and understand how we can solve this by doing a determinant, which we're already pretty comfortable with. Question?
So when you have in your matrices the H21, does that mean we need the H12 on the bottom row in the original E5?
Well,
equation?
yes, in this equation. So this equation has these two
'cause
elements are almost
equal,
always going to
so
be
they're
equal
just
to
all
each other.
okay.
I just made it really I made the most generic matrix possible there.
Okay.
So
Let's make sure we don't have to have that.
yeah. So and we'll see that we're going to be regenerating these equations when we put in some of our assumptions again. But what I want to point out is what we did here was we started with a guess function. We went through a bunch of mathematics. We generated this equation where we've got a bunch of integrals we could solve. And I want you to notice something about the structure of what I wrote down, which is essentially, we can look at this and if I multiply this E through, so if I put that E through, we can actually look at this way. I can look at this like I've got an E times each of these. This essentially looks like this. 1. Essentially, what we have done is we've reformulated our quantum mechanics into matrices. By the way we rearranged this using our guess functions, I'm defining this vector, the C1, C2 vector, was defined by my guess function, by my wave function. So I can call this psi. I put a squiggle underneath when I'm talking about these different matrix elements, these different column elements. This matrix essentially is an operator matrix. Each of these things is a wave function operator wave function represented in a matrix. So this essentially becomes like an operator matrix. And on the other side, I've got my same wave function column, my C1, C2, that's generated from my guess function. And then I've got some matrix that's going to describe my energy. And essentially, what I get back is E psi H psi. I get the same thing that we actually originally started with if I guess a linear combination of functions. And that's nice if we can solve all of these integrals. The thing that becomes important about this is I can then go ahead and subtract this matrix over, and I can rearrange this. So I'm going to take this S matrix, I'm going to subtract it over so I've got everything on the same side. And you essentially end up with H11 minus ES11, H12 minus ES12, H21 minus S21 H22 minus E S22 times some C1 C2 is equal to 0. In order to solve a question. Was that a question? No, okay. So essentially all I've done is I've subtracted this over so that one side is equal to 0, the other side is equal to this, and the question becomes, how do we solve two equations, two unknowns? Right? That's all. The whole reason we're organizing this into a matrix is so we can do two equations, two unknowns. And a lot of you are probably thinking, well, can't we just substitute and solve? You know, subtract down, do all that stuff. There's a lot of things we could do when we're just doing two equations and two unknowns. The question becomes, what do you do when you get to 3 equations, 3 unknowns, or 6 equations, 6 unknowns? MATLAB or matrix diagonalization, but how do you set that up in MATLAB? And you know, it's really nice that we have these computer programs to use, but we really have to set up the computer program properly, or it'll just sit there and get stuck in loops. So we have to make sure we're setting it up so that there's a problem that has a solution. And one of the things is when you're solving a series of equations like this, and you want to guarantee that you have what's called a non-trivial answer, there's one extra thing that is true. That is, we have a non-trivial answer when the determinant of our matrix equals 0. And I want to make sure we're clear about this. This is different than what we saw with the Slater determinant. In the Slater determinant, it had to not be 0. This is the secular determinant. This is for solving a series of equations. When we're doing the secular determinant, we want this to be 0. That's going to be the energy that we solve for. And I could put the E5s back in on these energies since we're doing the variational principle. That is what we solve for to make sure that we get a non-trivial answer to get some energy value. So this is for the most generic case of a guess function. I haven't said that my operators are Hermitian. I haven't said that my wave functions are real. I haven't said my wave functions are orthogonal or normal. Those are all extra things we can put in when we start saying, what are we actually going to guess? And this gets back to, well, what do we guess when we're doing the variation of parameters? And it really depends on what system we're looking at. So, this matrix is, I have a note to myself. I want to make sure I didn't forget it. The Hamiltonian is what's going to specify the problem. So really, whatever problem we're looking at, we still need to generate a Hamiltonian and say, what makes a good guess function for that Hamiltonian? What's the physical system? What are problems that we have solved that are like it so that we have a good guess function? What are some assumptions we can make that's going to simplify the matrix? And that is essentially, solving this matrix is essentially what we do for the rest of the quarter. Whether we're doing it for a 2x2, 3x3, 6x6, 8x8. Solving this matrix is essentially what we do for the rest of the quarter. Starting with the simplest case and then building up. And this is solving for some number of nuclei, some molecule. So for a 6x6, it would be the system that has 6 nuclei. So if you wanted to do like a benzene ring, not worrying about the hydrogens, just worrying about the carbons, you would have a 6x6 matrix. One element for each carbon, like one column for each of the carbon centers, looking at how those different wave functions representing those carbons could interact with each other. If you wanted to do something more simple, if you wanted to do a hydrogen, you would end up with a 2x2, right? You've got 2 nuclei, you're going to get a 2x2. And then depending on that system, we're also, depending on how we define the Hamiltonian, we're going to guess different functions that work with that. The most typical thing we do is we use the hydrogen-like wave functions. Because they're orthogonal, because they're normalized, because they are eigenfunctions of a Hermitian operator, and that's going to create simplifications. That's going to make things easier for us. But this matrix and generating this matrix, and the nice thing that's taken me a little bit more than like almost 2 hours now to get to, is we can generalize this matrix. The same thing that we did with the Slater determinant, where now we could go to n by n. We can do the same thing with the secular determinant and go to a broader application of this. So we don't need to, because you can imagine what a headache it would be if you wanted to guess a function that had 3 terms in it. You'd have to do 3 equations, 3 unknowns. You'd have twice as many derivative terms. It would be a real headache. Other people have already done that and said, hey, it fits with this pattern. You just add a 3rd column and a 3rd row, and that would be the 3 by 3 guess. Or you could do it for a 4 by 4 guess. Add a 4th column and a 4th row. That would be our next guess, next more complicated thing. So we can start building in complications relatively easily to this without having to do all of these like derivatives and these guess, like all of this part. We can really start jumping to this. So what's the simplest problem that we can look at that we could actually get a solution for that would be our first step along the way? 2 nuclei, 1 electron, right? Not a system that actually would exist. This would be the H2 plus molecule. So we can do the H2 plus molecule. And before we jump into the mathematics of it all, let's really just think about what that would look like. We're going to have nucleus A and nucleus B. They will be separated by distance capital R. Associated with them, and I'm going to put it off at a kind of funny angle, is the 1 electron. The distance of that electron from nucleus A is Ra. The distance of that electron from nucleus B is Rb. Right? And the reason we're starting with this simple case is you can imagine if you had 2 electrons, I'm going to have the electron moving, so that's going to be some 3-dimensional thing. I'm going to have the electron attracted to the first nucleus. I'm going to have the electron attracted to the second nucleus. I'm also going to have the nuclei kind of repelling each other. If, in addition to that, I had a second electron, you'd have a second motion term, 2 more attraction terms, and a repulsion term, right? So adding even 1 extra electron is going to add a lot of complexity, but it turns out that it's going to fall into this same type of system where it actually doesn't get much more mathematically. The integrals get more messy, but it falls into the same sort of framework of this secular determinant. Where now all we have to do is, diagonal minus the first diagonal minus the back diagonal to get our answer. So for this case, our Hamiltonian operator, not our H matrix elements, our Hamiltonian operator would be negative h bar squared over 2me del squared. And notice I don't need a 1. I'm only doing 1 electron, so I only need 1 kinetic energy term. Minus ze squared over 4 pi epsilon naught 1 over Ra. That's the attraction of the electron to nucleus A. Minus ze squared over 4 pi epsilon naught 1 over Rb. The attraction of the electron to nucleus B, plus z squared e squared over 4 pi epsilon naught 1 over capital R. The repulsion, and it's a plus term because it's the repulsion term, the repulsion of the 2 nuclei from each other. Right, so this is what we're going to look at. And I want us to start by just thinking about this in terms of the different kind of pieces that exist here. So if I ignored the second nucleus, I just ignored all of that, I've got a hydrogen atom. Right, you all see that? Cool. If I ignored these two terms, I have the other hydrogen atom. Right, so I essentially can think about this, and I want to do the conceptual work before we get into all of the mathematics. But I can think about this in terms of just having a 1s on A, or I could think about it in terms of having just a 1s on nucleus B. And really, if I wanted to consider all of this together, kind of the simplest thing to do would be to have a 1sa plus a 1sb. To think about putting these two separate cases together, that would make something that starts to look like a molecule. So I'm going to consider this. And this is going to be interesting for a couple different reasons. One is, even when I've got this 1sa case, I'm still going to have the attraction of this electron to the first nucleus and to the second nucleus. When I have this case, I'm going to have this electron attracted to the first nucleus, the second nucleus. Those are really going to be the same terms, but I'm going to be considering them kind of separately. And then the thing that's going to be interesting, so this is going to essentially be looking at like a Coulombic attraction, just the same singular hydrogen atom. And then I'm going to be looking at, well, what about this part that's attracting the electron away from just being a hydrogen atom with another hydrogen atom next to it, with a H plus next to it. And then I can look at the case of, well, what happens when this electron actually completely switches over to being in the other orbital? So rather than it just being attracted across to the other nucleus, it actually changes over to the other orbital. And so we're going to have different integral terms for each of these ideas that we can solve. That's kind of the conceptual work. And hopefully this kind of conceptual work gives you an idea that a good wave function to guess for this a good wave function to guess would be a C1. Actually, I'm just going to call it a psi 1sa plus a C2 psi 1sb. I'm going to use my hydrogen-like wave functions, those things that I've already solved, to say, yeah, that looks like a hydrogen. I've got some other junk that I have to take into account. That's why we're doing variation of parameters. But that looks like a hydrogen function. And yeah, that looks like another hydrogen function. So if we have this as our guess function, we get to use some of those nice things. Hermitian operators, orthonormal basis sets, stuff like that. And the part that we're going to be solving, and since we've got a linear combination, all of that work we did last time means all we actually have to solve I'm going to write it here so I can do a bunch of work on the other board. All I have to do is solve that determinant. And we'd have some answer that would give us some insight into formations of molecules. Notice that we don't have to do, when we write this down, I don't have to do like a 1sa1 with an alpha and a 1sb1 beta 2. We're not taking the spin part into account here because we're only doing a one electron case. we've only got one electron. We don't really need to worry about that spin part. We're not going to have electron exchange. We don't need to worry about the Pauli principle of anti-symmetry because we've only got one electron. So, okay. So with this guess function, we get to bring back some of our nice things. Some of the things that I had in our equations before that I said I wanted to have this be more generic. So again, we're going to use a couple things. Psi 1sa is normalized. Psi 1sb is normalized. H is Hermitian. Right? These are all going to be things that help us simplify what we are going to do. H11 is H22 on a different center. Right, that picture I erased before, if I'm looking at just a psi 1sb on B, that's going to be H22. That's going to be the same as psi 1sa on A, that's H11. We've got some symmetry there. We're thinking about the two different parts, thinking about the nuclei by themselves. So H11 and H22 are actually going to be the same integrals. The thing that's weird that we have to make sure we understand is psi 1sa and psi 1sb are not orthogonal. They're not orthogonal to each other because they have a positional offset, right? They're not on the same position, so they're not going to be orthogonal to each other. So we've got some simplifications that we can do to our matrix. I'm going to essentially simplify this matrix to be H11 minus E. And we can put that E5 back on there so we can remember what we're doing if you want to have that specific part. I'm going to have, oh boy, so much to do. I'm going to have H12 minus E S12. I'm going to have H21. And now I can finally switch this back to what we had before, H12 minus E S12. And then I can have H22 minus E5. I was able to get rid of the ES's here. So let's talk about some of the simplifications I just did. Let's talk about integral S11, and let's remember what that notation is representing. So S11, in this case, would be the integral of psi 1sa star psi 1sa d tau. This would be, if you wanted, r squared sine theta dr d theta to phi. There's only one set of coordinates for the electron. We're using the hydrogen-like wave functions, which are normalized. So we already know that integral without having to do that integral because we picked a normalized basis set, a normalized set of functions for guessing. That integral is 1. So I just have E phi, the S11 part is equal to 1. If I have S12, that's going to be the integral psi 1sa star psi 1sb d tau. That one I actually have to solve. I can't say it's nice. It would be nice if we could say it's equal to 0, but because of that offset, we can't actually say it's equal to 0. S21 is going to be the integral of psi 1sb star psi 1sa d tau. Now, the thing is, because this is just an offset by the nuclear coordinate r, these two functions are essentially going to be the same in terms of whether they're complex, not complex. They're just off by an offset. But this one's also off by that offset. So these two integrals actually end up being the same. Because when we write down the functional forms of these, they don't actually look different. And if we go through and do all of the multiplications, they don't look different. So if you want convincing of that, pull out your equation sheets for your hydrogen-like wave functions. Look at the n equals 1, L equals 0 case. And you'll see that that wave function is not complex, so the star part's not going to matter. We're just looking at, we're really going to be concerned about the radial part here. So the fact that we're using real functions, mostly focusing on the radial parts, that's going to be okay. The angular parts are going to work out in a very similar way. So the fact that these two things are equal to each other, that's fine. The thing that's nice about it is we just eliminated 1, 2 integrals. So we now only have 3 integrals to solve. We've got the H11, the H12, and the S12. Okay. So let's do, and I'm going to come back to these integrals. These integrals are actually not not fun to solve.
Would S22 be the same as S11?
Yes. S22 would be equal to the integral of psi 1sb star psi 1sb d tau. So if I'm centered on B and I'm using my wave functions on B, that's just equal to 1. So picking a normalized basis set gets rid of a bunch of the integrals we have to do. We still need to do this integral. And that integral is not pretty to do. I'll show you why that integral is not pretty to do by looking at H11 and H12 and talking about why these are such a mess. So let's jump to looking at our hydrogen-like wave functions. I'm going to get rid of all of those and just say that's something we still need to solve. S21 is equal to S22. That's something we need to solve. Let's look at the hydrogen-like wave functions. Or sorry, the hydrogen integrals that we have to solve. Using that Hamiltonian, okay, H11 has quite a bit to write up to it. I'm going to have and I'm going to split this up in a particular way. Right, so setting it up like this, just taking the first 2 terms in the Hamiltonian, I've still got to do the other 2. I'm just showing you why I'm splitting it up this way. That's hydrogen. That's the problem we already solved. That's the energy for a 1s hydrogen. However, I still have those other 2 terms on the end there. And this thing, that thing's weird. This thing is just hydrogen. That thing's hydrogen-like. If we look at this, this is just going to give us an energy of a 1s electron. We solved that a week ago. right? Psi star H psi. This is the H for a 1s electron centered on A with our wave function centered on A. Just looks like hydrogen. This thing, that's a problem. And there's a couple funny things that people do. They call this the Coulomb integral because you can see that we've got this attraction term of the 1s orbital over to the other nucleus. And we're also taking into account how the nuclear repulsion term is playing a role. So this just looks like a bunch of Coulomb forces, different from our hydrogen attraction that we solved before. And we just call this integral J. We essentially write another term where we're like, that's an integral we could solve. And I don't know if I want to admit this while I'm recording it, but I'm going to admit this. I actually did not look carefully at the way you solve this integral until this past weekend. I have always just taken the solutions that existed and been like, cool, it's been solved, let's move on. And after looking at how you actually solve it, I'm like, oh yeah, that's why. So in order to solve this integral, we have to realize that this RB term is essentially offset from the orbital we're trying to compare it to. So we have to do two things. We have to use the law of cosine. How many people are familiar with the law of cosine, 1 through 5? About half zeros, half fours and fives. So I'm taking it as people who took Calc 3 and people who didn't take Calc 3. Or is it Calc 4? Oh, so this is where, so the law of cosine is saying I have to deal with the fact that if I'm looking at my psi 1sa, I'm essentially looking at a wave function that's centered on A. And all the coordinates are relative to A. I have to figure out, relative to A, what the heck does this RB distance mean? And it turns out that through the law of cosines, I'm going to erase this stuff and do the new assumptions we're using. Due to law of cosines, we can say RB is equal to the square root RA squared plus R squared minus RA R cosine theta. Looking at this as some angle theta. So, and we're not going to do this. But I wanted to show you, I wanted to say there is a way you can solve this integral. We have to do two things. Oh, sorry, it bounced. We have to do two things in order to solve this integral. This one's easy. We're going to use the Born-Oppenheimer approximation. R is a constant. We're just going to get a constant. We're just going to have a normalization. We're just going to get a constant out of that. This piece, that's the tricky piece. And what we're going to say is, oh, I could use law of cosine, and I can rewrite RB in terms of RA, and a constant, R. But it's a square root of the thing you want to do an integral with respect to, because we want to do the integral with respect to RA. So now you've got the thing you're trying to integrate with in a square root. So then you all know what you have to do in that case. You're going to have to do U substitution, and I think you just have to do U substitution twice. You don't actually have to do integration by parts. But you have to do U substitution twice. And if we went through and did all of that, the thing that becomes really fascinating, the thing that I was like, oh my goodness, this is awesome, is when you do that, when you do the U substitution twice, you notice you've got a square root of RA squared. You're going to end up with an absolute value term. And you're going to split your integral into two parts, 0 to capital R, and then capital R to infinity. And all that matters to us in this class is we get an answer for this. We get an answer for this integral. We get e to the minus 2 capital R, internuclear distance, times the quantity 1 plus 1 over r, the internuclear distance. By doing this integral, and it makes sense, if we integrated this with respect to Ra, we should be able to get rid of our A component and just get some numerical value. If R is a constant, that whole thing, if I give you a value for the internuclear distance, it's just a number. Now, doing the integrals to get this, and I loved this. I was flipping through different textbooks. This textbook for solving this integral actually had this phrase. It is fairly easy to evaluate this integral. See problem 14. And problem 14 in that chapter said, oh, use your solution from problem 3 and problem 4 to show that this integral can be evaluated. It was like a 5-page problem. It was not easy to evaluate, as they say. But I'm glad that I went through the process and kind of have a deeper understanding of what happened. I'm not going to ask you all to do that, but the thing that I'm going to ask you to understand is the fact that this Coulombic attraction, only depending on the internuclear distance, kind of makes sense, right? All that matters for how this electron is being attracted to both is how close the nuclei are to each other. That should make sense. So, I'm going to go ahead and replace H11 here in orange with the equation we just did, E1s plus J, right? And that integral we can solve. If we add an internuclear distance, it's just a number. If we do the same thing, I'm going to try to do this right underneath this for H22, so you can see how H22 comes out the same. Oh, I shouldn't have erased J. Okay. So if we set up H22 right underneath it, I'm going to pick the way I organize things a little bit differently, but I'm going to get psi 1sb negative h bar squared over 2me del squared minus z e squared over 4 pi epsilon naught 1 over r b times psi 1sb d tau. Forgot my star over there. Plus integral psi 1sb star and z e squared over 4 pi epsilon naught 1 over r a plus z e squared over 4 pi epsilon naught 1 over r psi 1sb d tau. Notice the parallelism. I've got my E1s. Notice I'm doing it in terms of RB now. My orbital is centered on B, and my psi A is now offset by that same distance r, but in the opposite direction. This ends up giving us the exact same thing as H11. So H22, it turns out we can also replace with an E1s plus J. I can also erase the S22 because that's a normal set. And the J value is actually going to be the same because it is the same offset. Everything is actually the same between those two. All that changes is whether we're thinking about it in terms of centered over here and being attracted to there, or centered over here and being attracted to there, but the symmetry is still there. Those two things look the same. Question?
In that second Z term over there in the green, that should be squared, right?
Which one? Oh, yes, it should be squared. Yeah, that's because the charge of the nucleus is a ZE, and I've got 2 nuclei for my repulsion term. We often, well, for this problem, we don't really care because Z is going to be equal to 1. But if we're being generic, yes, Z squared. Thank you. So, we only have 2 integrals left to do. And because of the symmetry, we really only have, sorry, we have 1, 2, 3 integrals left to do. But because of the symmetry, we really only have 2 integrals left to do. The same way that h11 and h22 look similar, h21 and h12 are going to look similar. If we collect terms the right way, those two things will look the same. And s21 and s12 are going to look similar in the ways that we collect the terms. So let's look at h12. Are we ready for that? I didn't hear anyone shout stop, so I'm going to go ahead and see what happens for this next one. So, integral h12. We're essentially going to be looking at this. This one is perhaps the most interesting out of all of the integrals. If we look at this, h12 is going to be the integral of psi 1s a star negative h bar squared over 2 me del squared minus ze squared over 4 pi epsilon naught 1 over rb psi 1s b d tau. And I picked b because remember, this is my operator. It's going to operate on this wave function, not this one. So I wanted to make sure my operator lined up with this. This chunk is going to give me E1s psi 1sb, right? This psi 1sb is an eigenfunction of this operator. That chunk. But I'm still going to have an overlap integral left over, so it's not quite done yet. And I'm also going to have this really interesting integral over here, psi 1s a star negative ze squared over 4 pi epsilon naught 1 over ra plus z squared e squared over 4 pi epsilon naught 1 over r psi 1s b d tau. This one is weird. This part essentially simplifies down to be an E1s integral psi 1s a star psi 1s b d tau, which is just S12. We get S12 back out after we do this operation. So the first part's not that bad. The second part essentially gives us another one of these weird integrals, where now I'm going to have to do the same set of tricks, right? The center of my wave function is on B, but my operator is centered around A. So I'm going to have to use the law of cosine. I'm going to have to then do use substitution twice. I'm going to have to write psi 1s a in terms of psi 1s b or vice versa. There's essentially 4 different steps, 4 different math tricks we have to use in order to solve this integral. And I think your book calls it something different than I'm used to calling it, but I call this the exchange integral. Exchange integral K. I just want to check what your book calls it, because it was the first time I saw it called this, and I was like, oh, interesting. Dun, dun, dun. It's a K. Exchange integral K. It still uses this symbol K to represent it. The interaction between the nucleus and the extra electron density, but I cannot remember what your textbook called it. I can't find it. It still uses the symbol K in your textbook, but it used a different name for it than I use. And I can't remember what that was, but it's a fine other name for it. It made sense to me what they called it, but I just can't remember what it was. So I call it the exchange integral. And this integral has a solution just like the other part. So we, again, if we do all those math tricks, we're going to get something. It's going to have it's going to have this S12 in it, just like this has an S12 in it. It's going to have an S12 over capital R minus e to the negative R 1 plus R. But what I'm going to do is I'm just going to go ahead and substitute that in. I'm going to get an E1S, just like I had before, S12 plus K. Right? The K integral is also going to have an S12. It's going to have that S12 integral in it. But we get that. If we did it for the H12, we would change our B with our A. We'd do the exact same thing. You're going to get the same thing here. Energy for a 1s electron plus K. This gives us only one more integral to solve. The S12 integral. Question?
For the bottom left, S should be 2, 1.
Yeah, we can see it's not going to matter, right? It's actually, because of the symmetry of the problem, because of this idea, the two are going to be the same. So we're generically, yes, but for this case, we're starting to see that all of those things are actually the same. Our last integral, S12, in order to solve that integral, you have to do the same set of tricks. And I'm not going to do anything besides just tell you. I call this integral, I'm pretty sure everyone calls this integral, it's the overlap integral. It's essentially, if I looked at my two pictures of a nucleus, of an electron centered on nucleus A or an electron centered on nucleus B, what would it look like when those two things are overlapping? It's not 0 because they aren't orthogonal to each other. And if I wanted to get the numerical value for it, I'm trying to figure out a good spot to write it. I'll put it here. S12, again, has its answer in terms of just the internuclear distance. E to the minus R, 1 plus R plus R cubed over 3. How do we get that? You do a couple substitutions, you do a U substitution, use the law of cosine. It's a little bit burly. And again, I'm not often going to ask you to understand how to do all of that. But the thing I want you to notice is, again, the way it works out is my overlap integral, my exchange integral, and my Coulomb integral all end up simplifying to just being in terms of the distance between the nuclei. And if I'm thinking about an electron interacting with two nuclei, that makes sense. It makes sense that the distance between the two nuclei would give me information about how the electron is interacting with those two nuclei. The closer the nuclei are together, we're going to get some integrals be larger, some integrals be smaller, because you notice you've got an e to the negative r. So as r goes to infinity or as r goes to 0, we've got 1 over r's. So as r goes to infinity, r goes to 0, these components are going to have different responses. But we can look at this, and now we can actually solve this determinant, recognizing again that this determinant, these two other energies that I didn't change that are still in green, actually these 4 other energies, the ones that were still in green, those were all the variational energies, the energies that we were trying to figure out, the approximate energies. And now I can very simply do this term times that term minus this term times that term. Right, and I can solve it. So if I do my crossing, I'm going to have E1s plus j minus E phi squared minus E1s S12 plus k E phi S12 squared equals 0. Right? Because of this symmetry of the problem, and the reason this symmetry happens is not coincidence, is because of the functions we chose for the problem we were working on. But I'm going to have this times that, which is just that term squared. This times that, which is just that term squared. And this has to be equal to 0. So now all you have to do is solve that for E phi. Yeah?
Are we subtracting E phi S21? Or
Oh, yeah. Oh, sorry. There should be a negative there. Getting carried away. As I'm sure you can think about from looking at this, this is going to give us a quadratic equation in terms of E phi. And we can do a whole x equals negative b plus or minus squared. We can do the algebra. There's another trick we can use. Everyone sees it. There's another trick we can do where we can add this over, take the square root of both, start simplifying, but we're still going to end up with essentially, because we're doing the square root of squared things, you essentially still end up with a positive case and a negative case. And what we end up with, I can go through that process for those that are really curious after class, but I really want to get to what the point is here. We get two possible energies for our, and notice, we get two possible energies. These two possible energies, this is, one energy is going to be when we add, the other energy is going to be when we subtract. But these two possible energies represent what happens when we minimize this E phi. When we minimize this, yeah?
So do you have to do both adding and both subtracting?
Yeah, so we're going to define this in terms of an E phi plus, which is going to be the 1s electron energy plus j plus k divided by 1 plus s. And we're going to define an E phi minus energy, which is going to be the E1s plus j minus k divided by 1 minus s. So we end up getting two energy terms. Essentially, what we've shown here is by guessing, and I want to point something out important. Let me see. Where's that note that I had? I made a note to be like, we can write coordinates note, Coulomb integral. Oh, where'd I put that note? So the thing that I'm pretty sure. I knew there was something particular I wanted to say. Oh, the reason that we end up with two energies is because when we do this minimization, when we solve this secular determinant, we're doing it for wave functions that are not the exact answer, right? This is an approximate solution. And we essentially end up with a situation where we can have the interactions be in a constructive way or the interactions be a destructive way. Question?
Is that S in the denominator the same as the S1?
Yeah. This would be S12. We often, since S12 is equal to S21, and that's the one we care about, we often abbreviate it just S. But this is, for the notation I had up above, that is S12 for all of them. But for us, the overlap integral is always S12. So we can look at this and we can start to understand by defining our system and going through the process of solving all of the different integrals. Remember, both these energies, I've got my hydrogen-like energy. I've got something that only depends on the separation distance. and I've got my hydrogen-like energy and something that only depends on the separation distance. And essentially what we look at here is we've got something that's going to be that looks like a constructive interference and a destructive interference. Something that reduces the energy and something that increases the energy from the 1s energy. If we wanted to draw a picture to try and represent what's happening here, we might draw something where we say we've gone from having two 1s energies, and we often draw this a little bit a different way, and we've gone down in energy some amount for our E phi minus, and we've gone up in energy some amount for our E phi plus. We often, in order to draw this picture, we often draw the 1s orbitals that we're combining on opposite sides. And we get some energetic picture that looks like that. Wait, you want some electrons? So when I draw this picture, I heard a lot of O's.
Why didn't you just say so?
So keep in mind, what we were trying to represent was a molecule. And by guessing functions that were hydrogen-like wave functions, we've created some molecular type orbital. So essentially what we've started to do here is we've started with the simplest case, the 1s case. And we can look at how these energies interact with each other. We could take this further. We're kind of out of time. We just have a few minutes left, and I've been doing a bad job of giving us time to ask questions at the end. So I want to make sure I give people time to ask questions. But I got to the thing I wanted to of drawing this picture. Question over here and then over there.
So for the goal of an exchange mineral, will we give you those, or do we have to memorize?
Yeah, no, I would give you those. Right? Most of the time, and your textbook completely does this, we just leave them as J and K and say, yeah, you can figure those out. Right? So notice our 1s energy here. In any textbook I've looked in, my 1s energy, my plus and my minus energy are always written generically in terms of the J, K, and S integrals. They never actually solve them, which is why, until this past weekend, I'd never actually solved them. I knew they just depended on internuclear distance, but I never knew the process of actually solving them. Other questions? Yeah?
So, turning into a factor, like, what exactly are we going to be tested on? Like, what parts of this whole process?
Right,
Because
so
I'm just-
there's a couple different things that we can do, right? So on a quiz where we've got a little bit of time, it's going to be things like setting up the secular determinant, identifying which terms are symmetric, which terms are not, you know, setting it up so you can minimize and get the different parts together, recognizing the exchange integral and the Coulomb integral, some definitional kind of conceptual ideas. Unfortunately, most of the really deep, interesting mathematical things that we could do with it all are done with computers, right? Which is kind of mind-blowing to me because the people who first did this didn't even have calculators, right? They did it all by hand, and they figured this stuff out. And it makes me wonder how much, like, are computers stopping us from getting more interesting ideas because we're just like, oh, just do it in a computer? Or are they helping us get to, like, the most complicated ideas? And I don't know the true answer to that. Question?
Would a possible exam or quiz question be something like set up but don't solve this matrices for all possible, and then tell us if it's...
Yeah, it could be like set up, tell me what simplifying assumptions you could use, identify which integrals, you know, definitional type ideas would be most of it. That would be a lot of it, yeah.
So
Question here and then there.
what we're then want to be able to do with this is do this exact stuff again, but just know why it works and like how to say the
Yeah, so
definitions
we
of,
really-
like, set
we
this up
really-
and why would it be orthogonal or not? Like,
Yeah, so we really
able to
want
do
to
this
think
again
about
on our own?
why this process and what the important parts of this are. Recognizing how we can collect terms is really important. So there's quite a bit of this process we could ask about.
Was the collection of the terms basically like splitting your integral, like
Yes,
integrate what
how
looks like a
you split
hydrogen
your
versus
integral.
what's
So
a
recognizing
exchange or Coulomb
recognizing the Coulomb integral and the exchange integral is really just about how you
Do that.
split up your terms around your Hamiltonian. Question. This will not be on this quiz. This is like getting ready for the midterm. One last thing I want to mention. I know we're just like 25 seconds from ending class. The last thing I want to mention is, again, what we can start to do is we can start to expand this. We can add nucleus C. We can expand this in terms of adding a second electron and complicating these wave functions so they're like our Slater determinant type wave function. We can start to add in a lot of complexity. We can start to see how we modify our wave function and how we modify our Hamiltonian to get to pretty much any problem in chemistry. Question?
For the quiz, it's not cumulative, so it's from the midterm up until what we.
Yeah, it's from the midterm to essentially when we finish the sample problem on Thursday. If there one more question.
What would be a chapter map of that?
Oh my goodness, a chapter map. Yeah, did you email me asking about that?
Yes.
So if you emailed me since Friday and I haven't responded to you, come talk to me once I stop this video because I like fell behind on my emails. I know there's a couple people I want to talk to. So like if you've emailed me and I've done a bad job responding, please talk to me right now if you've got the time.